Lecture 8.4, Day 1, Improper Integrals. This is the Durango and Silverton Railroad, a tourist railroad in Durango, Colorado. A view of a water stop on the Durango and Silverton. Until now, we have been finding integrals of continuous functions over closed intervals. Sometimes we can find integrals for functions where the function or the limits are infinite. These are called improper integrals. Note that in this case, the word improper does not mean bad. It has a specific mathematical meaning. Example 1. The integral from 0 to 1 of radical 1 plus x over 1 minus x dx. The function is undefined at x equals 1. Since x equals 1 is an asymptote, the function has no maximum. Can we find the area under an infinitely high curve? We could define the integral as the limit as b approaches 1 from the left-hand side of the integral from 0 to b of radical 1 plus x over 1 minus x dx. This is a left-hand limit. We must approach the limit from inside the interval. To evaluate this integral, we're going to rationalize the numerator. We multiply the top and bottom by radical 1 plus x, and we get the integral of 1 plus x over radical 1 minus x squared dx. Now we can split this into two integrals. For the right side, we'll use substitution. We let u equal 1 minus x squared, du equals negative 2x dx, so negative 1/2 du equals x dx, and we see x dx in the integral. We recognize the left-hand integral as inverse sine x. For the right-hand integral, it becomes minus 1/2 integral of u to the negative 1/2 du. Evaluating the integral, we now have inverse sine x minus u to the 1/2. Then we back substitute the value of u and put our limit in, so we have the limit as b approaches 1 from the left-hand side of inverse sine x minus radical 1 minus x squared evaluated from 0 to b. Expanded, it becomes the limit as b approaches 1 from the left-hand side of inverse sine b minus radical 1 minus b squared minus inverse sine 0 minus radical 1. As b approaches 1, the inverse sine of 1 is pi over 2. As b approaches 1, we have 1 minus 1 is 0. The inverse sine of 0 is 0. So we get pi over 2 plus 1. This integral converges because it approaches a solution. Example 2. The integral from 0 to 1 of dx over x. This looks similar to our last example, so we might expect similar results. We can write this improper integral as the limit as b approaches 0 from the right-hand side of the integral from b to 1 of 1 over x dx. Notice we use a right-hand limit because we approach the limit from inside the interval. Taking the antiderivative, we have the limit as b approaches 0 from the right-hand side of ln x evaluated from b to 1, which is the limit as b approaches 0 from the right-hand side of ln1 minus ln b, this is the limit as b approaches 0 from the right-hand side of ln 1 over b, which is infinity, because as b approaches 0, we're taking the natural log of infinity, which is infinity. This integral diverges. Example 3. The integral from 0 to 3 of dx over x minus 1 to the 2/3. The function approaches infinity as x approaches 1. That's what the graph looks like, so it's open at the top. To evaluate the integral from 0 to 3 of x minus 1 to the negative 2/3 dx, we need to split it into two parts. We have the limit as b approaches 1 from the left-hand side of the integral from 0 to b x minus 1 to the negative 2/3 dx, plus the limit as c approaches 1 from the right-hand side of the integral from c to 3 x minus 1 to the negative 2/3 dx. Taking the antiderivatives, we have the limit as b approaches 1 from the left-hand side of 3 times x minus 1 to the 1/3, evaluated from 0 to b, plus the limit as c approaches 1 from the right-hand side of 3 times x minus 1 to the 1/3, evaluated from c to 3. Notice to find the antiderivative, we increase the exponent by 1 and multiply by the reciprocal. Now we plug in our limits of integration. As b approaches 1, 1 minus 1 is 0, so this term disappears. And as c approaches 1, once again 1 minus 1 is 0, so this term disappears. So we get negative 3 times negative 1, or 3, on the left, and on the right-hand side we get 3 times the cube root of 2. So our answer is 3 plus 3 cube root 2. Example 4. Integral from 1 to infinity of dx over x to the p, where p is greater than 0. P is a constant. We could write that as the integral from 1 to infinity of x to the negative p dx, which is the limit as b approaches infinity of the integral from 1 to b x to the negative p dx. Taking the antiderivative, increasing the exponent by 1 and multiplying by the reciprocal, we get the limit as b approaches infinity of 1 over negative p plus 1 times x to the negative p plus 1 evaluated from 1 to b. Or the limit as b approaches infinity of b to the negative p plus 1 over negative p plus 1 minus 1 to the negative p plus 1 over negative p plus 1. What happens here? If p is less than or equal to 1, then b to the negative p plus 1 gets bigger and bigger as b approaches infinity. Therefore, the integral diverges. But if p is greater than 1, then b has a negative exponent, and b to the negative p plus 1 approaches 0. Therefore, the integral converges.